Hi, my name is Kweku Adams. I'm a software engineer on the Android Frameworks team, focused on several of our battery saving mechanisms. We've made several changes to how and when apps can run tasks in the background, including in this upcoming release. Today, we'll be discussing some of those changes, why we made them, and some best practices for developers to run work in the background efficiently. Everyone wants their device to last as long as possible. A dead battery means no more communication with friends and loved ones, reduced safety, lost access to entertainment, and so much more. As such, battery life is one of the top concerns for users when choosing a device. Users download apps to get a job done. That may be to communicate with friends and family, entertain themselves with music and video, figure out how to get somewhere, or for many other reasons. Users get frustrated when things aren't working the way they want or expect. This includes things like delayed notifications, the app not being as responsive as it should be, or when the app appears to be draining excessive battery in the background. We all have a part to play in providing the best experience for end users. At the end of the day, users care about battery life, well-functioning apps that fulfill their expectations, as well as security and privacy. Developers want to reach users, provide value to their users, and in some cases monetize. The Android operating system in the middle serves as a platform that connects developers with users and must balance the needs of both users and developers. The system must measure and manage the resources each app uses, prevent abuse, but still give users ultimate control over their device. Our vision is to provide a high-quality, reliable platform for all parties involved. This means that the operating system must provide developers with consistent and well-documented API behaviors, making clear the constraints on the APIs and when to use or not use a specific API. The OS also needs to give developers the right tools to be efficient and as reliable as possible within their apps. The system must efficiently scale and allocate resources to apps to match the needs and desires of the user. And finally, users should be able to expect predictable battery life when using their favorite apps while not compromising on reliability. I'm going to hand off to my colleague Jing, who is going to go into what the Android team is doing in the operating system to help preserve users' battery. Let's work together to achieve the best outcome for users.
Thank you, Kweku. Hi, my name is Jing Ji, and I'm a software engineer on the Android Framework team. The Android team has worked on different pieces of the puzzle in pursuit of our vision, and each piece works together. Generally, we've been working to improve consistency across devices, increased user control over certain behaviors, made significant changes to file-based cloud messaging policies, and continue to improve job schedule behavior and functionality. We'll get things started by talking about how we are improving consistency across devices. Fragmentation is hard. Over the years, Android fragmentation has been very challenging for developers. App developers spend a lot of effort to accommodate the Android device manufacturers' customizations. One of the major motivations of device manufacturers is to offer better battery life to their users. To accomplish this, we've seen device manufacturers introduce various app restrictions, and they are often undocumented. This can make it difficult for app developers whose foreground service, for example, could work as expected on one manufacturer's device, but be killed unexpectedly on another. We understand the motivation of the device manufacturers, and we also see the frustration from app developers. To mitigate this problem, we're looking to standardize the app restrictions into a few levels, so apps would know what levels they are and what restrictions they could be facing. The levels start off with little restrictions and get more restrictive as we move between levels. Some of these levels are automatic, while other levels must be selected by the user. The first level is unrestricted level. User can choose unrestricted from the battery setting for a specific app. Apps that are unrestricted will receive few restrictions and could have a negative impact on battery life. For this reason, this is a level that can only be selected by the user. The next level is the optimized level and is the default setting for most apps. The optimized setting can also be selected in the battery settings for the app. The optimized level consists of the 4 app standby buckets we introduced in Android 9: active, working set, frequent, and rare. Each bucket receives a different quota for jobs, alarms, and other resources. The system will move the apps between these buckets according to their usage history. The more often users interact with their app, the more resources the system allocates to the app. The next level is the restricted bucket. We launched the restricted app standby bucket in Android 12 and will expand it as a new restricted level in Android 13. As you may know, apps in the restricted bucket receive very limited jobs and alarm quota. Thus, it is limited in the amount of background work it can perform. The last level is the background restricted level. In this level, apps are not able to have foreground service or do any other work while in the background. In this level, apps that target ADSDK API level 13 or higher will also see their book complete broadcast deferred. The background restricted level can only be activated when the user selects restricted from the battery settings for a specific app. Due to the severity of this level, apps may not function properly. Consistency is key. We continue to work with Android device manufacturers to improve background restriction consistency. As mentioned earlier, one of the major motivations for device manufacturers is to offer improved battery life for users. So we are trying to focus on the actual battery consumption of each application, especially background battery consumption. In Android 13, we're adding support to track the battery usage of individual applications across different dimensions: foreground, background, and foreground services. In addition to the new restrictions, Android 13 includes several improvements to Job Scheduler focused on battery efficiency and system health. First, Job Scheduler has improved how it handles jobs marked as prefetch, aiming to run them closer to next estimated app launch time. Jobs will be deferred to when they will be the most useful to the user and enable loading of fresher data, helping to reduce app loading time without running work too early or too often. Next, we also introduced a new priority API to provide Job Scheduler with more information it can use in its execution policies. When an app has multiple jobs ready to execute, the Priority API helps sort within the app's own jobs. The Priority API is not used to sort jobs between apps. Job Scheduler will also use this priority to know which jobs are appropriate to stop first when the system is low on resources or in a critical state. The new Priority API works with the improved response to device health to balance system health and app functionality. For example, Job Scheduler has improved its response to device thermostats, stopping job earlier to prevent the device from getting too hot. Job Scheduler will stop an app's lower priority job first, and then only start stopping higher priority jobs if the device keeps getting heat up. Some people may be thinking, why not just set all jobs to the highest priority? To that, there are 3 answers. First, it's not a good etiquette. We'll be discussing what we mean by etiquette in detail later, but for now, we will just say that is not an efficient use of the user's battery. Second, just like expired jobs, higher priority jobs have a shorter timeout than default and lower priority jobs. This discourages using higher priority jobs in the wrong situations. And the third, setting all jobs to the same priority provides no benefits. The system cannot distinguish between any of your jobs and one of your very important jobs that could be stopped to allow a less important job to run. This may reduce your job performance in the long run. Finally, repeatedly transferring the same data over the network is wasteful. Job Scheduler tries to be smart about running jobs when it has confidence that this job will be able to transfer all its estimated data. However, we know that some apps support pause and resume network traffic while others don't. So we are providing an API to let developers tell job scheduler the minimum amount of data they could transfer, indicating support for pause and resume, and allow job scheduler to better determine when the job should start. Set minimum network chunk bytes can be used with or without set estimate network bytes to help job scheduler be smarter when you are using the network. We also made improvements to expedite jobs, especially for apps running on top. This should make the switch from foreground service to expedite jobs easier. Many of these changes are about giving developers the tool to be good citizens and help the system manage the balance between device health and functionality. You may have heard that Android 13 introduced a notification permission. If you have not heard of it, be sure to check out the Developer Privacy User-Centric app Talk at I/O to learn more. While apps that are not granted this new permission will no longer be able to post notifications, foreground service can still run as before, but the notification associated with the foreground service will no longer be visible. As in previous version of Android, developers must still include notifications when start foreground service in the API call. Another feature that impacts visibility of notification associated with foreground service is that users are now able to swipe away these notifications. This has been a popular feature request by both users and developers, and we are excited to have it in Android 13. As we mentioned, foreground services must be associated with a notification. Notifications aiding the user's awareness that work is happening in the background. With these changes to notification visibility, it becomes much more likely that foreground services will run and the user can completely forget something is still running in the background. This makes foreground service more vulnerable to abuse. So, to tackle this problem, Android 13 is introducing a new affordance which allows users to stop foreground service from the notification shade, regardless of target SDK. We refer this new affordance as Foreground Service Task Manager. With the Task Manager, running foreground services can be easily recognized. Additionally, as you can see from the screenshot here, the Task Manager provides a stop button to allow the user to stop the app process hosting the foreground service. Unlike force stop, the app's jobs alarms will be preserved, so it minimizes the impact to the app's business logic. With the changes to notification visibility and the introduction of the Foreground Service Task Manager, Android 13 has given users more control over both notifications and foreground services. Android 13 will also be introducing some changes to how app standby buckets affect quotas for high-priority file-based cloud messages. Our long-standing guidance has been to use high-priority FCMs for time-critical user-visible messages. In previous version of Android, the quota for high-priority FCMs were directly related to the specific app standby buckets assigned to the app at any given time by the OS. Because app standby buckets are based on user interaction, basing the quota for high-priority FCM on app standby buckets were less than optimal for certain class of apps, which have lower user interaction but the need to notify a user. To improve a developer's ability to send high-priority display messages, Android 13 will be decoupling high-priority FCM quota from standby buckets. Developers sending high-priority messages that result in display notifications will see an improvement in the timeline list of message delivery, regardless of app standby buckets. Apps that do not successfully post notifications in response to high-priority FCMs may see some of their high-priority FCMs downgraded to regular priority messages. We encourage developers to check the priority as delivered by using remote message.getPriority before doing any work in response to an FCM. If needed, you can also check remote messages.getOriginal priority to confirm whether the FCM was always normal priority or if it was downgraded. Now I will hand it back to Kweku to talk about a different way developers can think about system resources.
Thanks for explaining all the ways that Android 13 helps preserve users' battery life, Jing. We'll be digging into best practices for developers, but before we give some concrete suggestions, first, let's discuss what we meant by etiquette earlier. Imagine that a friend invites you and a few other friends over to their place to help them on a project. When you arrive, you see a set of energy bars on the table. Your friend says each of you can have some of them to energize yourself throughout the day as you work on the project. Once you eat a bar, it's no longer available for anyone else to eat. The polite thing to do would be to take some and leave some bars for others to eat, including your host. In the same way, users invite you and other apps onto their device to get things done. Each app has a different task and must consume energy to complete the task. Different tasks may require different amounts of energy, and whenever energy is consumed, it's no longer available for other apps or the user to use until the user charges again. Etiquette would say to consume the minimum amount of energy required to complete the task. Anything that isn't required for the task the user requested should be pushed off to when energy is unlimited. This is a long-winded way of saying that resources on mobile devices are extremely limited, and that all of us, both the operating system and app developers, must be diligent to consume as little power as required to meet the user's needs and expectations. Now I'll hand it over to Vinny to discuss some ways developers can be more efficient in providing value to their users.
Thanks, Kweku. My name is Vinny De Silva, and I'm a developer relations engineer on Android, focusing on power and thermals. As Kweku mentioned, it's important for developers to practice good etiquette when consuming resources on a user's device. Next, I will be going into some of the practical ways that developers can reduce their power consumption. First, we are going to be focusing on battery efficiency techniques that improve battery consumption of background work. Afterwards, we'll even discuss some of the techniques that will be helpful to reduce battery consumption when users are actively engaging with your app. Work Manager is an Android Jetpack library that helps developers run work in the background. While Work Manager has lots of great features and benefits, today we're only going to be focusing on what it means for power. When it comes to saving battery, Work Manager intelligently uses the most efficient method of doing background work based on the parameters defined for the task. This is particularly noticeable when we compare Work Manager and using foreground services directly. Foreground services are very powerful and are tuned for performance, not efficiency. We encourage developers to consider Work Manager as an alternative. For time-critical use cases, use the Work Manager Sec Expedited API. And if you're looking to squeeze out a bit more battery efficiency with Work Manager, there are a few things you can do. First, be sure to perform any type of cleanup logic in response to cancellation signals provided via the isStopped and onStopped methods. Second, we recommend creating very smaller work requests grouped by the resources they need instead of creating one monolithic work request. For instance, if your work depends on a network connection, but only some of it needs to run on a metered network, split the work into two separate work requests, one for metered and one for unmetered network. This allows the system to optimize the different work requests based on resource availability. Another opportunity to improve battery life is to consider how your app receives messages. Have you ever been at an important event and a friend calls you and you think to yourself, gee, this really must be important. Let me step out and take this call. So you step out, you take the call and you ask, hey, what's going on? And your friend says, nothing. I just wanted to say hi. How would that make you feel? Well, that's sort of what it's like to receive a high priority FCM when it's not actually high priority. Developers should be diligent about using high priority FCMs for messages that are actually high priority. A high priority message is there for you to get someone's attention. It is very powerful, and you should use it wisely. The best way to determine this is to ask yourself if the message is appropriate to interrupt the user with a notification. If the answer is yes, then go ahead, use a high priority FCM. But if the answer is no, and the user can probably wait to hear about this later, just use a regular FCM. High priority FCMs will wake up the app when a device is in a dozed state and can take the CPU out of a low power mode. It can be pretty disruptive to the system's ability to manage power. So it's really important that developers only use high priority FCMs for things that the user needs to know about right away. and the changes that Jing discussed earlier support this guidance. Lots of you are building apps that work with external systems. Some of you get data on a web server, others are reading IoT data in the user's home, and some of you may be looking at stats provided by the latest wearable. These are all very important use cases that bring a lot of value to users. When doing this kind of work in the background, it's really important to make sure that apps are not refreshing data too frequently. For instance, is it really appropriate to execute a GET query to a server every second? Is it useful to read IoT sensors every 5 seconds? What about wearables? When talking about refreshing this type of data, I often like to think about what is an actionable rate. If I gave a user a piece of data now, this very second, after how long is it okay for the user to be notified that the piece of data changed? Is it 1 second, 5 seconds, 30? It's good to think about how often data should be refreshed while in the background. Efficiency points to finding the slowest frequency that is actionable to the user, at least for defaults. Refreshing data any faster than the user would do anything about that change is not an efficient use of resources. I understand that finding the ideal refresh rate for your data may not be easy. If that's the case, you can give the users an option to refresh their data quicker, but it's often a good idea to start with a reasonable default. For all the folks working on Bluetooth-enabled apps out there, it's important to be aware of the scan mode you are using. If your use case allows, consider using scan mode low power or scan mode balanced instead of scan mode low latency. This is especially important if you're performing scans in the background. Scan mode low power will use the battery most efficiently. If latency is critical for your use case, there are a couple of things you can do to reduce the battery impact of scan mode low latency. First, consider the frequency and duration of your scans. Reducing the frequency which you perform scans and the duration of scans can greatly improve battery life. If reducing frequency and duration does not fit within your use case, the other approach is to only scan while your application is being actively used by the user in the foreground. We talked about some of the ways that we can improve battery efficiency while performing background work on Android. I do have a couple of additional tips that might be helpful when users are actively engaging with your application. The first of these topics will be around responding to the device's thermal state. Device thermal state and battery consumption are often correlated. In other words, as a device consumes more and more power, the device is likely to heat up. Android has a built-in mechanism where resources such as GPU and CPU become increasingly limited as a result of increasing temperatures. This mechanism is referred to as throttling. As the system throttles more and more resources, there's an increasing possibility that your app's user experience will be impacted. For this reason, it's often a good idea for your app to observe the signals provided by the system. This gives app developers an opportunity to limit their resource usage before the system imposes restrictions at a lower level, which may result in poor user experience. For example, let's say that your app renders videos to users. If the device starts throttling CPU and GPU, it can increase the likelihood of video stutter or jank. Alternatively, if the same app uses the on-thermal status change listener to react to thermal signals, the app could choose to reduce the resolution, resulting in less resource usage instead of risking dropped frames. This is one example of how listening to the thermal signals can improve both user experience and battery life. We encourage developers to get creative and look for opportunities to respond to thermal signals in a way that align with their use cases. If your application uses the on-device camera, we strongly encourage developers to be using Camera X. Camera X is a Jetpack support library built to make camera app development easier. Camera X includes tons of useful features and benefits for developers. But did you know that Camera X is also battery efficient? Camera X is built on top of the Camera 2 APIs, which are much more efficient than the deprecated Camera 1 APIs. If your app is still using the Camera 1 API, moving it to Camera X will not only give your app tons of great features, but it will also improve battery performance. This last best practice is mostly geared towards game developers or apps that do any kind of specialized video decoding. Modern devices can have display refresh rates of 60 Hz, 90 Hz, or even as high as 120 Hz. These devices are capable of displaying incredibly smooth animations. However, games and apps that only render at 30 or 60 frames per second on displays that refresh much faster can lead to jitter, jank, or other visual artifacts. These artifacts can be prevented by setting the display refresh rate to match the app or game's refresh rate. Setting the display refresh rate with the Surface.setFramerate API to match the frame rate of your game or app will not only improve the animation quality, but it will also improve battery life. If you're using a game engine, be sure to check their documentation for APIs that set the display's refresh rate. Today, we discussed many best practices that you can implement in your app to help users feel a little bit less anxious with their battery. From using Jetpack libraries such as Work Manager and Camera X, to being careful with how you communicate with Bluetooth devices and other external systems. The ecosystem as a whole benefits when batteries last longer. I appreciate your time today, and I will now hand it back over to Kweku to close us out.
Thanks, Vinny. Following those recommendations will help make your app more efficient and improve the user's experience with their device. We understand that many changes come suddenly, and repeatedly rewriting portions of your app is a large burden. So we want to share our philosophy and how we're thinking about future changes now, so you can be better prepared and start working to future-proof your app early. As we noted with the energy bar analogy earlier, resources on mobile devices are extremely limited. Once battery is drained, it's no longer available to anyone, including the user, until the user charges again. For a long time, we have had policies that effectively allowed the concept of infinite work, despite finite resources. Recognizing that resources are actually limited, we will continue to tweak our policies to better reflect the limited nature of these resources. We will continue to invest in improving the operating system's efficiency in order to reduce its own power use. We'll also continue to work on standardizing and improving consistency across device models to make developing Android apps easier. Finally, we'll provide more APIs and tooling to help you do the right thing as efficiently as possible. You can help by auditing and prioritizing the work your app is doing, trying to push off things that are more deferrable to when more resources are available, such as when the device is charging, and by letting us know what use cases are not well supported and what APIs you believe will help you build better and more efficient apps. We hope this helps give you a glimpse into where we're heading and enables you to build more efficient and delightful apps. And remember, with great battery power comes great responsibility. Thank you.